event. And kicking things off here, you can see that we're in the first session here in the AMER region. And if you scroll down, you can find information for all of the sessions that we're going to be doing. So this is day one of 3 sessions. And we're going to be kicking things off with a little bit of an introduction on Nextflow, jumping into our first script with Nextflow, and then spending the rest of the day looking at a very basic RNA-Seq pipeline and some sort of dependencies. So just to kick things off, my name is Evan Floden. I'm the CEO and co-founder of Sakara Labs and one of the early members of the Nextflow project. I'm going to be running you through the introduction to Nextflow. And I'm going to be handing things off to Marcel, who's also here, and he's going to be taking things over from there with the RNA-Seq pipeline. I'd like to stress a couple of things. So it's a live session. We do have people in the Slack room, and that's the best place you want to join if you want to ask questions or follow along with the conversation there. If you scroll down, you'll see a section in here for asking questions. So we're on the 3rd one here, this training October 22 AMER. And if you select that, you should be able to find the channel inside of the NF Core Slack. So if you click on this link, if you're not part of the Slack already, you can go into there. You'll find everyone they're sort of hopefully chatting away and sort of asking questions, and hopefully you get some benefit as well from seeing questions that other people are asking as part of that. So I'm going to kick things off with a bit of a small presentation on this. And just in terms of prerequisites, you don't need to have anything installed or anything to follow along. All the material that we have is available online. And we're going to be using a Git pod environment for all of the actual code. So Git pod has got a live coding environment. We can spin that up. It's got a Nextflow and all of the resources and data and scripts, etc., installed in there. And from there, the only thing you really need is an internet connection, a browser, which I assume you've got from here, as well as a GitHub account for logging into that. So we're going to got quite a bit of material to cover today. So without sort of stopping too much, I'd like to jump into the first set of slides and just give you a little bit of overview of Nextflow, kind of discuss a little bit the problem that we're trying to solve with Nextflow, as then I'm going to dive into some of the kind of theoretical background for what's going on. We're going to cover, say, a lot of material the next couple of days. It's going to start off with some things where you may see some, so this is a gentle introduction, but also maybe see some repetition of the things. So don't worry if you don't catch the concepts first time. Some of these things just take a couple of times of seeing them and a little bit of practice as well to get going with that. So without further ado, kicking things off, let's discuss, and starting off with basically the problem definition of writing a sort of a modern scientific pipeline. Here's an example of an ancient DNA pipeline, which is very timely given the Nobel Prize, which got awarded earlier on today for looking at ancient genomes in here. And this is a pipeline which is from NF Core. You can see that if we think about some of the characteristics of what this is, we've got lots of different tools here that we're trying to essentially chain together, as well as kind of orchestrate the data through that pipeline. So in bioinformatics, we've very often got a whole bunch of different tools from different sources. Maybe you've got something from GitHub, some script you've written yourself, maybe even some proprietary software, some containers from all over the place. And you have to kind of pull that all together into essentially a piece of software which you can rely on. On the left-hand side here, you can see that we've got some data which is going into it. And bioinformatics itself is, and most of the life sciences, is sequencing data is very sort of file heavy. So it's usually big, large files. And those in themselves present some kind of challenges to how we're going to process these. And we don't just want it to work on our computer or onto even our environment. We really want to be able to take these analyses and share them. Maybe we want to take them and sort of scale them across different environments, or share them for publication, or even at least just make sure that they are reproducible in the kind of broader sense of the term as well. So summarizing the problem, we all have sort of larger and larger data sets which need to be processed and which we need to get some sort of answers from. These can be sequencing data, imaging data, larger sort of more structured data sets as well. And within the bioinformatics sort of pipelines and within the tools that we've got, we often end up with this problem or embarrassing parallelization, where we want to run our pipeline, but we want to run each sample through that pipeline, or we want to run, for example, taking our genome and splitting it by chromosome, and we want to run each chromosome through that pipeline. So you end up with this parallelization problem where you're essentially splitting up your work and you're running that maybe tens, hundreds, thousands of jobs over some sort of distributed compute. It's typically the kind of analysis that you can't maybe do on a single machine or on your laptop, and therefore you're sending it out to a cluster or to a cloud. And we have this kind of big mashup of different tools, as I mentioned before, from all sorts of different resources. Now that creates a bigger problem in terms of sort of managing all the dependencies there. Like typically the old style way, you'd have to go install each piece of software, and you'd spend so long just trying to kind of get that going, or you could move on to the next step. But with the advent of containers and systems like Nextflow, a lot of that has become a lot easier. So that's kind of, again, some of the core problems trying to solve in this regard. If you think about it maybe from a more kind of goal-oriented perspective, everyone's heard of fair data. And we like to take FAIR and sort of apply it a little bit more, not to the data itself, but to the data analysis. So the idea of making our analysis findable, and this is kind of principles of open science as well, that we're making these things, your pipelines can be available from GitHub or different repositories as well, that they're accessible and that they can be used by everyone. There's no real limitation on the fact that we can spin up environments now pretty much at will for everyone to use and to run. Obviously, the interoperability is key to this, whether we're running in cloud or in cluster, all these different systems, and Nextflow is a big enabler of that. Reproducibility, I'm going to stress a little bit in a moment. This is a key tenet of Nextflow and a key part. And then sort of like we've expanded out FAIR a little bit to include now equitable, scalable, that you can run the same analysis from your laptop onto a supercomputer, as well as test it, really using modern software engineering practices. And you'll see later on with some of the NF core pipelines, we've got some unit testing in there. We sort of recommend always having a small test data set as part of your workflow, your pipeline that you run through. And you start to apply some of these good practices using Git, for example, into all of the work that you do. And that obviously pays off a lot when it comes to making your software more robust. Okay, so when I mentioned before about all of the different pieces of software you have to install, this is an example of a pipeline. I'm going to say this is a genome annotation pipeline. So it was like looking at parasites and trying to annotate their genomes here. You can see each of these little circles. Hopefully you can make it out in the live stream, but there's each little circle is a piece of software or process. And you've got these black arrows which are going on between them. And those black arrows are essentially directing the data. That the data comes from one process into another. Maybe there's a transformation that occurs, and sort of installing and managing all of this software, it's a real hassle. So kind of a key example of how trying to do this in sort of the pre-workflow manager era was a real kind of nightmare to take care of all of this. And this is an example of the different pieces of software and tools which need to be put together and to run. Obviously, that presents a big challenge, not only just to usability, which is of course the key part, but also like reusability and going further than that, making the whole thing reproducible. So here's an example of a paper that looked at taking the idea of a computational science paper, basically a computational biology paper, trying to replicate it based on just looking at the methods that are provided, all the information provided from the authors. So when you've got software numbers, versions, command lines, etc., even when that's all provided, it still makes it very difficult for a typical person to kind of reproduce those results. And here I say spending a couple of months trying to do that. And obviously most people are not going to spend 2 months just trying to replicate the same result of a paper, but it provides a kind of a challenge to us. And if we think that we're going to be basing so much of the work that we do on the results that are coming from this kind of analysis, maybe even outside academia, if we think about the applications in the clinic, etc., it's not really something that we want to be relying on for doing. There's got to be a better way than describing our work, describing our science, and describing our analysis in this kind of way. So the problem is even worse than that a little bit, though. So even though that we may be able to, say, reproduce or got the same software versions, we know exactly what the pipeline's doing, even in those cases, still be situations where the same workflow essentially gives us different results or different results depending on the environment that we're using. And this is what we showed early on in the sort of the Nextflow paper, was we looked at a couple of pipelines, including one that I showed you before, the genome annotation pipeline. And we saw that we get different, essentially the genes were annotated in different locations. So you can see here that depending if we ran this in Mac or in Linux, we ended up with a start sign with these genes being differently located. as well as we did a transcript quantification with Callisto and Sleuth, so very common tools, very simple pipeline. And you were seeing that the genes that were called differentially expressed were different depending on if it was Linux or Mac as well. And obviously that presents, again, some big challenges to us. Even when we've got everything sort of controlled for, and to a certain extent, we end up with these differences. And this is likely down to underlying changes or differences in the libraries and kind of the low-level code. Things that sort of very hard to control for, particularly before the use of the widespread use of containers as part of the work that we do. Okay, so Nextflow provides obviously a big solution to that, and just going and sort of now providing us some sort of background on how Nextflow works with regards to that. So Nextflow is obviously solving the reproducibility part, and a lot of that's coming from the containers. But the kind of wider problem in Nextflow is solving here is in a concept, we have a language, so we have a way to write the pipelines. And that's what you can see in this top section here. So Nextflow is a syntax, it's a language. You can take code from any other language. So you can take your R scripts, you can take your Python, you can take your Bash, and you take those pieces of code and you essentially link them together with this data flow programming model. Now, we're going to be spending a lot of time looking at command line tools, but it's exactly the exact same thing, whether you're running command line tools or other tools in here. The concept is that you're wrapping those essentially sections in these process blocks, linking them together, and then defining all of the containers with all of the dependencies with containers, I should say. All of that gets wrapped in a Git repository, and it's from there that you can take any Nextflow pipeline and then run it in any environment. So Nextflow is both a language as well as the runtime. So those two things are linked together here. And it's really from that, the idea that you can take any pipeline and run it in any environment, that a lot of the community sort of aspect of Nextflow comes in, because it means that people can come together independent if they're running in Azure or if they're running in their local machine, or maybe they're running with a Slurm cluster. The whole code base is exactly the same. Those people can work on those code base, really contribute to it, and then run the actual execution in their environment as well. So how does it work, and why is Nextflow a little bit different, I say, than some of the other workflow systems out there? Because there is definitely many out there. Nextflow is a DSL, so this is a domain-specific language. It's a language written on top of another programming language, and that other programming language is called Groovy. It allows you, for the most cases, for 99% of the times that you need to write things, you have access to this domain-specific language, which is specific for writing the pipelines, makes it very easy to define processes, to define the key parts of your pipeline. If you are in cases where essentially there's something which is not in Nextflow, which you need, of course, you can write an issue on GitHub, but you can also access the underlying programming language. So you can access Groovy or even Java underneath if you need to get yourself out of those corner cases and account for those situations. Nextflow also has this reactive programming model, and the reactive programming model is where the data flow part comes from. And here, the data is essentially pushing or was kind of flowing through the pipeline, and reactive in the sense that the processes are reacting to that data. So that the processes are sitting there waiting for the data. Once it's received, they're reacting, and they're actually submitting their tasks or emitting those tasks as well. This will be seen in practice a few times later on. Very early on, we made a decision to keep Nextflow as this kind of concept where each task is self-contained. What that means is, in practice, is that each task lives in its own working directory. It's essentially its own unit of compute in a way. And as part of that, it means that each task could very easily become containerized. And this actually was slightly before the use of containers in this. So it was a kind of advantageous or fortuitous decision in doing that. But this has really led to many of the systems which have been built afterwards, things like AWS Batch and the managed services in the cloud, etc., all fit this model very nicely. And finally, as I mentioned before, this concept of keeping the workflow definition separate from the execution, the configuration of where you run those pipelines as well. So I'm going to show you here an example. This is a DSL1 example, and I'll point out that we're going to spend the rest of the workshop on DSL2, but this is purely just to show you the linking between the two processes here. So this is a task, BWA mem task. So this is a simple thing you may see sometimes in a script, or maybe you're running from the command line. To use this in Nextflow, we can keep this thing exactly the same. So the idea is we're not trying to recode it, or we have to define exactly what we've got. We're going to wrap it in what's called a process block, where we define the inputs, the outputs, and then the script section itself. And just looking a little bit at this, you can see that we're defining the input as a reference file, a FAST file, a sample queue. And then the key part is that we're going to take, when the task is finished, we're going to take the sample.bam. This is the output here, which is generated from this task. And this is the piece that we care about. We're going to use that, say, downstream from here. You'll notice that we've got something which may be a little bit different to you is this concept of these channels. So you've got from the genome channel, from the reads channel, and then into the BAM channel. What that's doing is those are the definition of those channels, which are the things that are going to link together our processes. Now in TSL2, they're not explicitly written in the process, but they're exactly the same. They're just happening behind the scenes, and we'll see that. The purpose of this, though, is that if I wish to use now my BAM files, essentially downstream from this, I can take the output of the aligned sample and use it as the input of my index sample test, of my downstream task. And this kind of link between these two things is what kind of drives the execution. So when this pipeline starts, both of these processes essentially begin. They're set there, they wait for their inputs. The first process on the left-hand side here is going to receive the sample and the reference. That's going to send, it's going to essentially submit the BWA task. Once that's completed, the sample BAM file will enter into the BAM channel and then be driven into this second process here, which will fire off the execution. And of course, this whole thing will happen in parallel and sort of across the whole pipeline as well. So these channels here are kind of a key driver of that. We can visualize this in a couple of ways, as we'll see some examples in a moment of this. In TSL2, and this is what we're going to be seeing, you can see you've got the definition of the process on the left-hand side. It looks very similar. We're just missing these this from and this into. And we can now we can essentially reference when we want to run, in this case, the quant process from inside of this workflow script. So you can see that the quant process takes the index and the read pairs channel. And we'll see this several times over the next couple of days. With regards to data flow, I said to mention that the key part of data flow is these channels. And these channels are what we call first in, first out queues. This is the kind of asynchronous first in, first out queues. This is the kind of name to them. You can think of it that the channels are really linkers between the processes themselves. And they're the kind of thing which are essentially connecting those processes so that they're firing off as soon as data enters into them, and that the correct data is received inside of that. Often this is better seen a little bit in practice. So if you consider here, we've got a channel which has got 3 elements. Now, these elements could be values, they could be files, they could be whatever you want. In this case, we've just got 3 elements outside of this channel, data X, Y, Z. And you can see that we have a process, and this is like the process definition, like we saw before. And the fact that we have 3 elements in here means that we're going to have 3 tasks be emitted of that process. So each task is essentially a sort of an execution of a process in this case itself. And then in itself would be generating some outputs as defined by the process itself. What does it look like? So imagine that you had, for example, a single file here inside of this channel here. In this case, we're just creating a channel called samples channel. Because we have a single file here as part of this, when we execute this pipeline, fastQC would run once. But if I was to expand that out and said, actually, my channel now contains all of the sample, all of the fastQ files, then from there on, the fastQC process would run as many times as I had files as part of that. And likewise, all the way kind of following through the pipeline as well. Here's a slightly different view on the same thing here. And it's just providing this parallelization is coming about in that manner. So now jumping gears a little bit and just considering that syntax and the kind of some differences that you see here between some other workflow tools. So Nextflow itself, compared to CWL, has this concept of being the language and the runtime tied together. It has this idea of being able to use this DSL on top of it versus just sort of being a YAML specification sense. We like to think Nextflow is a little bit more concise and fluent, so it's easier to read from top to bottom, get an understanding of of what's going on, as well as this concept that we have a single implementation so that the runtime is very tightly tied to the syntax, and those two things can really result in a lot of quick iteration and quick development process as well. On the comparisons with SnakeMake, obviously Nextflow is a lot more similar to SnakeMake if you're familiar with SnakeMake. Here the main differences is that Nextflow is using this push model, this concept where we are using this reactive data flow model, whereas SnakeMake is sort of the opposite. It has to start from the bottom, essentially build up the DAG. Sometimes you have to wait a little while for that DAG to be built, and then it will sort of start the execution, whereas Nextflow is kind of starting from the top and pushing down. In terms of support for the container runtimes, so Nextflow's had support for 4 or 5 at the moment as well, and it continues to expand. And the support for AWS Batch, Google Cloud, Azure Batch, etc., I think is kind of well known for having that kind of support as well. Okay, now sort of setting the syntax aside, considering now how we can run the pipelines. And over the next couple of days, we're going to be doing mostly local execution. We're going to see a small section tomorrow where we're looking at the different deployment models with regards to configuration and how you can run that. When you're running the pipelines, typically we're submitting with a local executor. This is just Nextflow run, and this is the kind of default way of running. The tasks run on your local machine, on the local operating system, using the containers or not. So that's optional, how you can set that up. And then you're using local storage for that. So this is most common for development, but also if you're just running a big box, like a single virtual machine that you just want to run everything on, you lack a little bit of the ability there. You get this kind of fine-grained control of the individual tasks, though, because in situations maybe different resources or you have a very large pipeline, you can end up waiting a long time. When it comes to cluster orchestration, Nextflow has support for 10 or 12 or so of the major schedulers here. So things like Slurm, LSF, Grid Engine, etc. And here Nextflow submits each task to the cluster itself. So it wraps all of those tasks in the correct, say, into a Slurm job, and then does the bsub command, for example. And in this case, Nextflow is really taking care of a lot of that. And then the actual scheduler itself will place that onto the actual compute nodes. The compute nodes typically here will have some sort of shared file system that Nextlow's running. And this is a pretty typical setup in an academia or some large organization where you've got a lot of compute resources. What's become really popular in the last few years is these managed services in the cloud. So this is an example of AWS Batch, but the exact same thing exists now for Azure Batch and Google Batch. It's very similar. In this case, Nextflow submits each task to the cloud provider's API. And from there on, the individual API jobs will spin up some virtual machines, depending on the resources that are required from those tasks. And then from there, the individual task will then run on those virtual machines. The great thing about this is that you can spin up resources as you need. So maybe data's coming off a sequencer, or you've got a whole bunch of analysis you need to run in one time. Maybe you need to access GPUs or some very large memory machines. And all of that can be done now by basically splitting up those resources in demand for those jobs as well. The kicker here is that typically the storage that's being used there is object storage. So you can think that these VMs are located all the way around this very large data center. Maybe the connection that they have for the individual input and output files is different. So they're being able to essentially being able to use that some sort of object storage is key, and we have quite a few solutions around that as well. Finally, there's Kubernetes. This is something maybe more for the future or for teams who have already got that infrastructure set up. You obviously now, instead of being a managed service, you have to manage, like, for example, the horizontal scaling here, but it's something that we see going to be a very key part of the future execution of the pipelines as we move towards a more cloud native approach to all of this. How does that portability look like? Well, here's an example. If we take a Nextflow script and we just run local, like this is what we're going to be doing in 5 minutes or so. We're going to say Nextflow run, and we're going to run that Nextflow script on a local machine here. It's going to run by itself. If we then wanted to take that same script, and notice how we won't change any code of it, we will simply add into a config file that we want to run on Slurm, that we want to use a queue here, 8 gigs, 4 CPUs, etc. You can simply add that in, and Nextflow will now wrap each task as a Slurm job and submit it in this way. And likewise, if we wish to switch out and we wish to run that same job in AWS Batch, the same thing can happen here, and we can see that we've got these abstractions for the concepts of queue, memory, and CPUs, which makes the pipelines very portable across different environments. A lot of that portability is really made available because of the fact that we decouple these two things, both the configuration and the actual workflow definition, as well as containers. And as I mentioned before, containers are kind of key to the reproducibility, but also to the portability of the pipelines. And the way you can think about this is that the containers themselves were typically developed for long-running web applications. There's kind of the key application is say running web servers, for example. But what we can see is we've essentially taken containers and tried to use them more for the use in data pipelines themselves. Earlier instances of this where people were trying to and still do to some extent, using virtual machines to sort of define all of the dependencies that are required for analysis. There's some disadvantages to this, though. The virtual machines are typically very large, so they're very big, they're difficult to move around. You've got this kind of slow startup time in terms of how long. So this is what we call the cold start problem. If you try and spin up a VM, you'll often have to wait 5-10 minutes for it to start versus a container which can spin up in seconds. There's also this idea of all the tooling which is available. So containers, and in particular the Docker tooling that came out, really allowed us very easily to build containers, to have registries to store them in, and we've got this concept of composability, so we can make layers, we can build on top of other containers, which really just makes them fantastic for the kind of work that we do. And there'll be a session later on today where we'll start to build some containers and show you that. As far as Nextflow is concerned, Nextflow treats each task as this kind of independent unit of compute. And so that led very well to the adoption of containers. You can think that Nextflow submits each task as a job. Each of those jobs just becomes a container in itself. And really from there, they can be scheduled out and submitted to different execution engines. All of the managed services in the cloud now sort of use containers as their kind of default way. And if you think about something like AWS Batch, it kind of sells itself as a container batch service. So it kind of lends very nicely to that. Nextflow also has support for other container engines, and there's actually a lot of interoperability between the containers themselves here and the ability to convert them. So going towards these kind of standards helps a lot for all of the work that we're going to do. When to use containers? Well, I would say always. Once you get used to building these, this is a really big advantage to your work. You're really helping your future self as well. Often in part of the pipeline, we'll define how we build those containers as well. And with things like GitHub Actions or other kind of CI/CD work and DevOps tooling, you can build those containers on the fly now. So it really becomes very, very easy and a sort of manageable way to take care of your environment as well as your code. And then, of course, the data itself, which we will see later on. As part of Nextflow's growth, it's on the community side, it's really been growing quite dramatically. A lot of that growth, I say, comes about because of this connection between these two things, between the execution environment and the definition of the workflow. This is a little bit out of date. I think we're up to 12,000 or so now developers who are working on Nextflow. And this is, again, just looking at the contributions of the runtime. But if we consider more broadly with Nextflow and then NF Core, it's a lot sort of bigger use cases there as well. If you're looking to get into Nextflow and editing, there's a couple of editors which are available. These are syntax highlighters. In fact, we're going to see one in a moment as part of our training that we're going to look at for Visual Studio Code. And finally, as I mentioned, NF Core, which is available here and something that we're going to spend a lot more time on day 3, where I believe Phil will come in and Harshil will provide a little bit more information on that. But with that, I'm going to head back over to my screen here. So just if you bear with me, I'm just going to change over to my screen here. And we're going to jump into now the practical exercise, the practical part of this. And if you go either into the Slack channel, there'll be people pasting some links here. But the key point we're going to see is we're going to go to this training material, which is at training.sakera.io or sakera.io/training. Or if you type in Nextflow training, you'll see it as coming up as one of the first hits on Google. Is on this website here, we have everything available. And this is going to stay here as well. This is public, so you can use this. All of the material, and in fact, this whole repository, that including the environment, is available over in this NF training public Git repo. So if you want to put any pull requests or you have any suggestions for the material, please feel free to have a look here. And the other kind of key resource that we're going to be looking at here is obviously the Nextflow docs. And if you have any questions on things as we go through here, there's always the Nextflow documentation, which is always good to sort of get familiar with in terms of learning how to read it. And hopefully we'll see the key concepts as we go through, which should make it easy to find information as you kind of join your journey. Okay, as I said, we're going to be using Gitpod for this, and Gitpod has got everything we need for the environment. What I am going to do, though, is show you how you could do this if you don't want to use Gitpod. If you want to install Nextflow yourself, there's a couple of requirements for Nextflow. Nextflow requires a POSIX file system. So this is essentially Linux, Mac OS, or also Windows subsystem for Linux. And the two main requirements are Bash and Java. So with those two things installed, you can pretty much get going. There's also Git and Docker, which are used for this workshop. As well as a couple of exercises here for if you want to use AWS Batch, for example. There's this Batch CLI and a few things. But for our case, we're going to use the Gitpod environment, so everything is set up there for you. If you go to 1.2 on the left-hand side there, what you can do is you can select this link here, which says click the following URL. And what this will do is it will spin up a Gitpod instance, which is essentially a container running in the cloud. And you'll notice that it's actually just the same repository as this. So it's just the same repository with this gitpod.io at the beginning of it. And what that does is that essentially, because of this file that we have in here, this .gitpod YAML, it's going to spin up everything that we need according to this. So it's got Nextflow installed inside of it. It's going to have our container already. It's going to have, for example, the syntax highlighting for our VS Code extensions and all of these things. As well. So I'm going to give you just 30 seconds or so to go through, find 1.2.1, and we're going to select that there, and then that's going to spin up. It's going to exit my previous one here, and it may ask you to log into GitHub, so you can put your GitHub login there. It's going to give that a few seconds to go through. I'm just going to find the training again. Let's go to here. Okay, you can see mine's just spinning up now. Just give it a few seconds. Okay, and now we're all good to go. Okay. So on the left-hand side, you can see that this is you've got like a file browser. So if you're familiar with that, kind of this is with VS Code, it's kind of got this option here. You can select these other things, but for the most part, we just need this Explorer. I'm going to shrink that sometimes. So that's just by clicking on this Explorer button, just to give some more real estate for you. And I'm also just going to, personally, just going to increase the screen size a little bit. So you can see a little bit more of my screen as I'm typing here and see this information. On the top here, you can see a space for file browser, sorry, for a file editor. And on the left-hand side here, you can see, sorry, down the bottom here, you can see that we've got some terminal. So if I do ls here, you can see all of the material that we have. We've got some data, we've got some scripts, we've got some config, everything's sort of available in here for us to get started. The first script that we're going to be starting with, though, is a hello world script. And I'm going to start with the training to go through this and show you exactly kind of what this looks like. I can move this to the side here and do that here. Let's go from here. Okay. If we look at that, and this is going to be starting from the section Your First Script. So if you're all set up with that, you'll see in Your First Script, this is an example which is, it looks a little bit trivial to start with, but there's quite a few things going on here. It's to try and give you a little bit of a flavor of the different elements of a Nextflow pipeline. So we're going to start by looking at, we've got some parameters, we've got the definition of a couple of processes, we're creating some channels, we're actually doing an operator, we're manipulating those channels, and we've got these various elements of that which is available to us. In terms of what the pipeline does, it's hopefully very simple to see here. And I'm going to run through it without Nextflow. So I'm going to show you how would you run this without Nextflow prior to doing it, so we get a feeling for what's going on. The basics of the pipeline can be described as taking a string, in this case, hello world. We're going to print that to the screen with this printf here. And then we're going to split the string using the split tool. This is a Unix tool which is available on your machine. And from there, it's just going to create for us some files, which is just going to contain the text itself. And the reason for this is creation of files, the parallelization and the parallel processing of files is something that we see often in pipelines as well. The next step down is that we're going to take those files themselves. We're going to cat them, and we're just going to take them and turn them from lowercase to uppercase. So in our case, we're going to take hello, make it uppercase, world, make it uppercase, and then we're going to print that to the screen. So it's fairly easy. There's to say trivial what the pipeline is doing, but hopefully we can get a bit of a feeling for how that works. So I'm going to show you firstly without Nextflow itself. So you can imagine that the first process is simply saying printf here, and then it's taking hello world. So hello world here, allow the copy, and then we're just simply piping that here to this tool split. Now, what's happening here, split is saying I'm going to split that string into 6 bytes, so 6 characters here. So you can think 1, 2, 3, 4, 5, 6. So the first one is going to be hello. And then the second one is going 1, 2, 3, 4, 5, 6. So world. And then what this is doing is this is saying, okay, put that with this prefix chunk. So this is going to create 2 files, which are both prefixed by chunk. This is just a kind of convention here. So when I run this, if I do ls now on chunk, you'll see that we have 2 files, chunk AA and chunk AB. And if we do a cat on them, we see the contents of them. You can see we've got hello and we've got world here. So that's all the first process is doing, taking the string, splitting it into 2 files, and basically making those available for us. Now then, the next process downstream of that is all about the parallel processing of those files. It's about taking those files and then using them for something else. In our case, we're going to say cat here, the actual files themselves. If you look at, just a quick reminder, if you look at this process here, we could even copy this if we wish, put this in here. And I'm simply going to replace now the Y with the actual file name. So chunk AA. And you can see it's taking it from hello to uppercase hello and lowercase world to uppercase world there. The final part of the pipeline is some Nextflow syntax around how we're going to basically be viewing that, how we're going to view the contents of that, which is essentially printing it to the screen itself. So now that we can kind of know, now we've got a feeling for, hopefully got a feeling for what we want the pipeline to do, or what at least the Unix commands of the pipeline are doing. What about the Nextflow part of it, and how is Nextflow handling all of this? Well, in the first case, we have a shebang here, which is something you often see in many scripting languages, just defining that we're going to be running this as a Nextflow pipeline. We have, in this case here, the params greeting file, which is a parameter. Nextflow has a special scope for parameters. They're treated slightly different. They allow us to do this sort of parameter assignment here. So we're saying we're creating a parameter called greeting. In our case, we're giving the default value, which is a hello world. And parameters can be defined in many places. They can be defined, for example, in a config. They can be defined from the command line. They can be defined as a parameter file. And all these different varieties of ways of allowing us to modify those parameters, sort of make it useful for the way that we want to use those pipelines in the future as well. The next step that we've got is the definition of a channel. And this is for the first time we see what's called the channel factory. We're creating a channel called greetings channel. This is, again, is like an assignment. So greetings channel equals this channel params.greeting. This is all kind of just basically just saying this channel contains a string for our purposes. We can then see that we've got the process definitions. In this case, the first process is defined as taking a value. This is just meaning a value itself. In our case, a value is a string, but it could be an integer. It could be any kind of basic data object. The key difference is that this is a value. This is not a path. So Nextflow typically just treats those two things differently because of the way that we have to treat sort of file objects versus we have to treat every other basic object, which can easily be passed around. So the way that this runs is this takes, in this case, our string as an input. It does the X, essentially performs this on the string. And you'll notice there's $X. And the $X here is this is a Nextflow variable. So we're assigning to the string this X value. And if this could be Y, this could be whatever you want to call this, whatever you call this here, it has to be shown here. This is what this kind of mixing of programming languages. Now you can see we've got some command line, and then we're mixing this up with a Nextflow variable, and all of this kind of gets interpreted when it's run. And then finally, you've got this output. So when this is run, when this task is complete, when there's essentially a successful exit code, what you'll see is the output will try and capture this. So it will capture chunk underscore star. Anything which matches that, any path which matches that, will be the output of this process. And then downstream from this, we have convert to upper. And in this case here, convert to upper, instead of taking a value, takes a path. So we want convert to upper to take a file as an input or a path as an input. And what this does is it takes that file, it cats it when it runs this. So just prints it, essentially, takes the contents of that file, I should say. And then it's just piping this here to do this transformation of taking it from lowercase to uppercase here. Finally, all of this is captured in the output here. And in this case, instead of being a value or a path, this is just a special one, which is a special output qualifier, which just captures the standard output. Whatever is printed to the screen here is going to go inside of this channel. So you'll notice that we've defined the processes here. So you've got these two processes, but we haven't actually referenced them. We haven't actually, the processes are not actually linked. This greetings channel is not linked to the process. And this is one of the things around DSL2. So in DSL2, you can define processes. They can even be in different files. It can be all over the place. And you've kind of got this modularity. So you can then reference them inside of a workflow section. So I can say the workflow itself contains, or what I want this to run, I wanted to run split letters on this greetings channel, which is going to create for us the letters channel. So the letters channel here, in this case, is going to be the output. The greetings channel here is the input, because you reference basically the name of the process. And the input, this has got one input, so it's this one here. And then the next step, we're going to take the letters channel, which we know now contains our files here, and they're going to be inside of the convert to upper process. So convert to upper is going to be running in here. And then we're going to do a flatten. I'll show you this later on, but this is our first example of an operator. And finally, the results channel, which is our standard output, the screen is essentially just going to be printed to the screen. Don't worry if you don't get all of that. That's basically like all of the kind of key parts of the Nextflow pipeline explained to you all in 30 lines or so. So let's go through and start running this to get a better feeling of what's going on with regards to this. There is a full description of every line as well in the notes below if you wish to see that. So what I'm going to do is I'm going to open up on the left-hand side here the hello.nf file. So open up that. It's on the left-hand side here, and you can see that we've got the exact same pipeline you should see. If you wish to edit this, you can just change the code there, and you can press Control-S to save that or to do this. Let's just get things running to begin with, and I'm going to say Nextflow run, and then I'm going to just say point to the file itself. So I'm going to write hello.nf. And when I do this, we can see so it comes through here. It just takes a few seconds to launch up. You can see we get the version of Nextflow that we're running. You can see where we're launching this local file. We get this name here, and then we get this revision. You can see that we had 3 tasks which ran. They all ran locally. We're running directly on this machine. And we get split letters, which ran once. And we get convert to upper, the process which ran twice. Let's do this again. See what we get. So now I'm just pressed up, and I'm just running the exact same code here. Notice here, now we get hello world, whereas before we had world hello. But why is that the case? Well, what's happening here is that the convert to upper process is running twice. So we can say that we got 2 tasks of convert to upper running, and they ran in parallel. And they ran in parallel like at the CPU level. What this means is we don't know exactly which one is going to finish first, essentially which one is going to be printed to the screen first, because of that really true parallelization. And this means that we can get a different order in terms of the way that they are printed to the screen here. And this is extremely powerful when you think that you may have tens of thousands of samples which you need to process. And each one of those may be running in parallel, let's say not on a single machine, but potentially say across a cloud, with hundreds or thousands of tasks running at the same time. And all of that enables this parallelization just because there was essentially there was two files that were generated to begin with as part of that. The other thing that's interesting to look at here is these letters at the beginning. And this is what we call the hash. So these are hexadecimal letters. They are what they call the task hash, and they are unique every time you run that task. And every time you run that task, and if you don't change anything, and you're not using resume, I'll show you in a moment, then this is like a unique hash here. The other thing about it is that this actually defines where the pipeline task runs. I mentioned before that each Nextflow task sort of runs in its own working directory. And from that, I'm just going to quickly remove my working directory here, and then do the same thing, run through. And what takes place here is when I run this, and if I just do a quick tree here on the working directory, you'll see that we have inside of my working directory, I get 3 sort of subdirectories which are created, and inside of that, those other 3. And you'll see that these correspond. So you'll see that split letters has 8349. You can see that 8349 was created, and that's where the files are themselves. So the individual task is actually run inside of there, and the files which are generated from that task are there. We could also notice that in the subsequent downstream process, that the actual files are, in this case, symbolically linked. So for example, the convert to upper task here, this 36E1 is actually pointing to the original location of the 8349. This 8349 there. So that in this case, because it's a shared file system, there's no need to pass the files around. And this whole point, this is why I was stressing before the difference between value and path, because when we have value and path, it's a very different from the way that we treat these things, and hence why Nextflow can handle these things, particularly in cloud environments where you need to be very careful about where the files actually are when we're referencing them versus just normal objects which we can pass around. Okay, now let's consider what if we wanted to make some changes here. So I'm kind of happy with my pipeline. Let's say I'm kind of content with how this is running, but maybe I wanted to make some changes to the second process. So we've got split letters, it's working fine, but imagine I made a mistake here and convert to upper. Instead of transforming that convert to upper, in this case now I want to simply reverse the file, reverse the contents of those files. Instead of being uppercase, I just want to reverse this now. What happens if I want to do this, but I don't want to rerun the pipeline from the beginning? I don't want to wait to do all the processes. Now, this is a trivial example because I showed you it takes a second to run. But in cases where maybe it takes days to launch a pipeline, this is obviously not an ideal situation. What we can do is we can do exactly the same as we had before, but we can instead of now specify resume, so Nextflow run hello single -resume. And when this runs here, you'll notice that the first process, this first task of split letters is cached. And what this means is it hasn't actually run that task. So if that task was going to take 2 days, essentially would just be cached here, and we don't need to rerun the whole thing again here. You'll notice that the second process, though, convert to upper, has run. So that's actually the piece which is run because we've made some changes here. And you can use resume whenever you want. So I can just leave resume on. In some cases, maybe leaving resume on is the kind of default behavior that you want to have. In this case here, when we leave resume on, because I haven't made any changes to the pipeline, you'll notice that everything is cached here. So the whole pipeline is essentially not had to run. It's used that caching mechanism for that. And what happens if I look now a little bit deeper and I say, if I look at the split letters process, you'll notice it's got this hash 8349. 8349, the hash remains the same. It's actually the hash is a key defining piece that Nextflow uses to know whether to run that pipeline again. That hash is made up of the actual input files. It's made up of this timestamps on those files. It's made up of the script section. This is the piece I changed here. And all of that comes together to know whether to change that as well. Okay, so far this pipeline that we're running is really kind of simple enough, but it's only for us, it's just running the this hello world piece. What happens if I wish to change this now? If I wish to say update this, so I'm not just running hello world, but I want to run it on my own data. Maybe I've got my own data. I come around, you've given me this pipeline, or we should run them this way. And with this, we can simply set up and we can say Nextflow run, again, everything is the same, hello. But now if we wish to reference or change this parameter, parameters can be changed using this double dash here. So I can say double dash greeting, because this is the name of the parameter. And from the command line, I can override that. So I'm going to change it from hello world to bonjour le monde here. And with this, we can print this. And now, instead here of when it launches, you can see that the first task is going to be very similar. Split letters is going to have 1 of 1. But convert to upper now is having 3 tasks. And the reason for that is that if we take bonjour le monde, we can split it by 6 characters 3 times and not simply 2 with hello world. And this again is showing a little bit of the data flow parallelization. So if I was to do the exact same thing and I just said whatever here, for however many times that I can split, in this case, this thing, however many files I'm creating, or how many files I'm starting with, I'm ending up with this parallelization. And here you can see we end up with 10 tasks being run for that as well. So something that's kind of, again, useful for driving that forward. Okay, let's consider one other thing which I didn't dive into yet before I hand you over to Marcel, and that is considering what's taking place with this flatten here. I didn't mention it so far, but I want to examine basically what happens if we remove this here and just have a look exactly what the letters channel really is. And this is something which can be very useful when you're trying to debug your channels or debug your pipeline. Simply write view on the channel and see exactly what's taking place here. So I'm just going to go back to the default one, Nextflow run hello. And what actually is the contents of that channel? The question I'm asking is, what is this? And you can see here that the contents of this channel is 2 files. And those 2 files are the 2 chunk AA and chunk AB files that we saw originally. You can see that they're both in the same working directory because that task is being executed from that working directory. But importantly, when I look at them, you'll see that we've got these square brackets. And that square brackets and the fact that they're on the same line indicates that they are a single element. So we could describe this as the letters channel contains a single element. And that single element is both those files together. The problem this has is that if I was to then take this originally, I'm going to remove flatten here, which is essentially doing the exact same thing. So I'm removing flatten. And when I run this, you can take a guess of what's going to happen here. What's going to happen is that the letters channel now, because it contains a single element, convert to upper just runs once and essentially runs on those 2 files together. So flatten in this case is taking, look at it again, you take the letters channel, I'm going to now flatten it and do a view. And I want you to look where the brackets are now. You'll see here that we no longer have the square brackets. And this means that every file, every element that we have every file that we have is a new element. So the fact that we have 2 elements now means there will be 2 tasks which are generated. And likewise, the same thing, if I was to show you here, like the example here, you'll see that every file that gets generated with this one that creates 10 files, every file that goes all the way down here, you can see we've got all of our different files here, would be processed in parallel, and that'd be processed in parallel using this on this convert to upper process as well. There's a little bit more of a description of what's taking place in the pipeline here. You can see all of the different pieces of that. Otherwise, feel free. I haven't had a chance to check some questions, but I'm sure there's lots of questions going on with regards to that. Very basic pipeline. Don't worry if you didn't capture all of this. We're going to go through now a RNA-Seq pipeline where we're going to see many of these same things again, but maybe a little bit more applied to bioinformatics. And then later on tomorrow, so the first thing tomorrow, we're actually going to go through every one of the processes. So we're going to look at how we make processes, how we make channels, etc. So you're going to see these things many times over the next little while, but this is just a little bit of a primer on the kind of main basic pieces of that. So with that, I will pass you now back over to Marcel, and I believe there's going to be a 10-minute break or so, and to take a breather. And then when we come back, we're going to take on the simple RNA-Seq pipeline, which is a great example of using some real data, some real FASTQ files, some FASTA files, as well as some real software where we're going to be doing some alignment as well on that. So thanks for your time, everyone. I'll pass you back over to Marcel now, and see you again shortly.
Okay, everyone, so now we're going to have a 15-minute break, okay? And feel free to use this time to go to Slack and ask questions, try to redo some snippets that you had some questions during the presentation by Evan. So in 15 minutes, we're going to be back. Hello, everyone. So let's go back. So I'm going to share. This here. So we are back to Gitpod. Okay. You've seen the first two sections with Evan. So now we're going to talk about this section 3 and section 4, as you could see before in the schedule of the training. Okay. So the idea here with this section 3 is that we're going to build a full, even though simple, RNA-Seq pipeline. Okay. So the idea is that we're going to really build like step by step using a few things that you have already seen about Nextflow and some things that you haven't. If you get a bit lost or confused during this, don't worry, okay? Because the idea is that we're going to show you like a full pipeline. We're going to build it together. And in the next sessions, like tomorrow, you're going to understand bit by bit, and then everything is going to be clearer. So the idea here, don't focus too much on the details about Nextflow, but focus on the idea of how Nextflow can make this pipeline work. So we're going to build 7 scripts, okay? And basically what they're going to do is that it's a bioinformatics pipeline, okay? It's an RNA-Seq pipeline. We're going to index a transcriptome file. Then we're going to perform some quality control, then some quantification, create some report. So step by step, okay? Okay, so let's start. So the first thing, as you saw previously, we can come here in NF training, and the scripts are here, okay? And here's just the training.secure.io that we've seen before. So my name is Marcel, okay? I'm the Nextflow and NF Core developer advocate for Latin America. So I'm hired by Sekera Labs, which is the company that created Nextflow. And one of my goals is to grow the community in Latin America. So if you are in the region and you need some support, either if you are like in a startup, a biotech company, or university, in academia in general, feel free to get in touch with me for support, for some help that you may need, some tips, some explanations about Nextflow, and of course, if you want me to give a talk or a training, just reach. Any conversation would be great. So the first thing here is we're going to start with the script 1.nf, okay, which is pretty simple. And in a way, it covers something that's been already shown in the previous subsection with Evan, okay? So we see here that we have a parameter which is reads, which has a path to a pair read here to reads. We have a transcriptome file, it's a path again, and a multi-QC path, okay? And then basically what this NF file is going to do, there's not really a pipeline here. It's just going to print the content of this variable, okay? So we can click here to open this script 1.nf. I'm going to increase a bit my, okay, some zoom here so it's easier for you. Basically, we're going to go to the terminal. And we're going to run this script 1.nf. So basically, it's going to print the content of this variable, okay? With this part at the beginning. So reads, we have here the project year, which is where the NF file is, okay? So it's workspace, NF training, public, NF training. And then followed by this path, which is where our FASTQ files are. So one thing we can do, basically, is to, since it's a parameter, as you saw here, this reserved keyword, let's say, you can set it with the reads. And there's something very interesting to know. So if you do Nextflow -h, you're going to have the help from Nextflow. And all the parameters you're going to see, they have one single dash, as you can see here. So whenever you were wondering if you should use 1- or 2-, so 1- are options and parameters for Nextflow itself, the Nextflow engine, okay? And 2-, they are parameters for pipelines, as the ones that we've seen here, okay? Read, transcriptome file, multi-QC, and so on. So what we're going to do here is going to run again, basically just going to print, okay? But we are setting the read, so we are not using the default values that you have here, okay? So again, it's just going to print, nothing new. But then let's, instead of just using that, the parameters that we have already in the file, let's try to add a new one. So we're going to come here to the script1.f. I'm going to use the editor that I like also. Script1 is bin. I have to zoom out a bit. Okay. I'm going to add here a new one, which is out here. Directory where I want files to be saved, even though it's not going to do anything, just a variable that I'm setting. Okay. And basically what I'm going to do is just add like results. So in the current directory, create this one. Another thing we can do is to start adding some information, not just say where the reads are, but information about the pipeline. Okay. So here, I'm going to copy paste to make it easier. Okay. And I'm going to stop here, just show you something. So once that I add this new parameter, which is out there, I'm going to add this log info to print to the screen a few things. So it's going to say what's the transcriptome file that I'm using, in this case, which is the default one. So if you set it, the user, when it's running your pipeline, he's going to see the transcriptome file that you set, okay, or the default one, the reads and so on. The thing is that if you run it this way, it's going to be a bit ugly. So as you can see, it's kind of pushed to the side, which we do here in reality, but for readings like indentation. So what we have to do to have the info like really tied to the border of the screen is that we're going to use this strip indent. Okay. So by using that, okay, we're going to strip the indentation, and then our information is going to be really close to the border of the screen, which is usually what command line software do, right? Okay, that's the first thing. So here's a very beginning. We cannot even call this a pipeline because it's not really doing anything. It's just getting some parameters and printing to the screen. So what we're going to do now is really start doing a pipeline. We're going to create a process, which is the atomic unit of some working that you have to do with Nextflow. So every task is a process being run. Okay, so we're going to create here a task called index, which, as we said at the beginning, is going to create create an index from this transcriptome file that we are providing. Okay, so this is already in the script2 file. Okay, so it's already everything we did before. So as I said, we're gonna build like step by step, and these next script files they're gonna get together with the final pipeline in the end. So everything we've done so far is still here, and now we're gonna create this index process. So a very simple process has basically 3 blocks. We have an input block, which says what are the input channels that are entering this process. We have an output block, which is going to say what's leaving from this process. If we are writing to a file, if we're writing to the standard output, which is the command line, for example, and what this process is going to do. Which, because usually we have multiple lines, we are used to have the multi-line string, which is the 3 double quotes. Okay, and here what this process is going to do is to call the Salmon binary, the software, okay, to create an index. We're going to give some CPU, some transcriptome file, and then we're going to the index that we create is going to be called Salmon index. So basically that's the process. But just defining the process doesn't run anything. You're just describing how a task would be, but you still have to call it. And that's the thing here, like how you're going to call it, what process you're going to call first, what process is going to be the input or output to another process. So that's the workflow block. In here, you're going to say how things will be run, in the sense that how process will be called, okay? So here we're going to call the index process, as you saw, okay? We're going to give as a parameter, and here you see there's an input, which is a path for the transcriptome file. So here we're going to do that. Params. This is an argument for this function, this process called index. And the output of that, we decided to store in this variable, which we call index_ch. So this _ch, it's not mandatory, but it's a good practice to let it very clear in your code which variables are channels, okay? So it's a good practice to add at some point at the beginning or at the end this _ch so that we know that this variable is a channel. In here is an output channel for the index process, okay? So once this is all understood, let's run this. So I'm gonna run Nextflow, run script2.nf. So one thing is gonna happen here. So what, let's wait a bit. what's going to happen is that Salmon is not installed. So it's pretty clear here with the message, right? So Salmon command not found. So Salmon is not installed. And here that's not error, actually. We made it this way because what we want to show you is that you don't need to install everything in your machine or wherever you're going to run your pipeline, either if it's in a cloud or a cluster or your local computer, your desktop, laptop. You can use containers or other tools that can help you isolate your environment. Okay. So here what we're going to do is that we're going to run with this parameter with Docker. And as you can see here, because it's one dash, it's a Nextflow option. It's not a pipeline one. So indeed, if you go to the script2.nf, there's nothing with Docker in here because it's not a pipeline argument. So we're going to do it again. Nextflow runs script2.nf, but now we're going to say with Docker. What's going to happen now is that Nextflow is going to create is going to run a container image with Docker. And this container image has Salmon inside, and that's why it ran just fine. So we can find, based on the hash that we see here, we can go there and see that we have all the files created by Salmon, okay? But then you might be asking, okay, so Nextflow knows that we want it to use Docker, but how does it know what the image and how is Salmon installed? So there's a file called nextflow.config, okay? And inside this file, you can provide some information, some configuring information about Nextflow. That's a very nice feature because in your script file, in your pipeline file, you write specifically about the pipeline. And any other configuration, you come to this nextflow.config file. And here what happens is that we're going to say that all the processes are going to run with a container, which is in the namespace Nextflow, and the name of the container image is RNA-Seq.nf. So we didn't say anything here about, I mean, because we say with Docker, here is in the Docker Hub, we didn't say anything, so implicitly it says it's on Docker Hub. And if you go to Docker Hub with the namespace Nextflow, you're gonna find this RNA-Seq-nf container image that we created, and we put Salmon inside of it. So not always you have to create your images. Sometimes there are already images the way you want, ready to use. In this case, there's this one for us. So that's how Nextflow knows which container image to use and how Salmon is installed inside. And that's why this command here, it worked, okay? If you don't want to all the time keep typing this with Docker, what you can do is that you can go to your nextflow.config, and at the bottom, you can do Docker enabled true. So some people, they do a typo sometimes and use enable, and it doesn't work. So it's enabled with a D in the end, okay? So by doing that, we can both use the with Docker if you want, but we don't need it anymore because we enable Docker by default in the Nextflow config. So now as you're going to see, there will be no command not found because it's using Docker by default. And you can do the same thing to other container technologies. For now, let's just focus on Docker. So you saw at some point here in the code that we have this, let's open this. As you can see here, when we were calling Salmon, we were giving some variables, which are CPUs, this variable CPU. And here, by default, it's going to be 1. But the thing is, you can say how many CPUs you want to request the operating system to use. So what you can do here, you can simply come to the beginning of your process, and you're going to specify CPUs. There are many other directives. So this is a directive. These optional configurations at the beginning of the process block are called directives. So one example is CPU, but you have many others, like Q and so on. Here we can say 2, and automatically when we run that, it's going to set to 2 instead of 1. And actually we can see what's going on. So we're going to go to our work directory. We're going to use the hash that we know where things are. And you can see the command.sh. And as you saw here, this is what's being called inside of whatever, the virtual machine, the container environment, the container technology, the container image. Here, it's going to be run with the 2 that we set, the CPUs. Okay. Another thing you can do is actually to see the channel. That's something that Evan did a while ago. And we can do just the same. So at the end here, we are just writing to the path with all those files that you saw a few minutes ago. But not only that, I want to see what's inside this channel. Okay. So I'm going to use the view operator. So these functions that we apply to channels, we call them operators. Okay. So we're going to use the view operator. Nextflow. Let's see what's going to show. So we have the path. Okay. This is very close to what Evan did when he was presenting a while ago. We already did this with the tree to see what was inside. So now it's a question that someone asked in Slack a few minutes ago before we came back, actually. In bioinformatics, very often we have this para-end sequences, right? So how we do that? How can we read that in Nextflow in a way that makes sense? It's not messy. So now we're going to go to script3.nf, okay? And we're going to see that not only the parameters are being provided to call for the processes, even though here we don't even have a process, but you know what I mean. So basically what we're going to do is that we're going to create a channel. So we're going to use the channel factory from file pairs. So Evan showed some channel factories. We're going to see many more like tomorrow. This one, basically you're going to give a path and it's going to understand you have file pairs actually. So by looking at this params reads, it's the first line here, we see that we give a path starting from our project here, okay? And then at some point it gets to this, which is a blob, okay? So actually if we go to data, you're gonna see here that we have gut1 and gut2. There are two files. They're both samples from the gut, here from liver, here from lung, but they are parent sequences. So here we have two samples, okay, for the same, two files for the same. So what we're gonna do is that when we have the script 3, and here we have this blob saying it's gut1 and gut2. And when we use the from file pairs, it's going to understand that. And it's going to do something which is very nice. So there's something I'm not sure someone asked a few minutes ago in Slack. So we're going to have a tuple. Okay, didn't print anything. So we're going to have a tuple, which is the first element here is like a key, okay, which is gut. And then the second element of the tuple is a list of elements, which are the files. Here, there are two, okay, it's a pair end. Each file and an identifier of these files, okay? Now, instead of just using the default, okay, so as you saw here, if you go to script 3, instead of using the default, which is just gut, we're going to set in the command line all the files there that end with 1 or 2. Okay, we're going to have gut, liver, and so on. So as you can see here, now we have 3 tuples because we have 3 elements in this channel, in this pair. Okay, we have gut and the 2 files, liver and the 2 files, and lung and the 2 files. Okay. One interesting thing that some people do, instead of setting a file, a variable name, a channel name, and equal to the name of to the rest of the expression is going to evaluate that, the channel factory. Some people they're going to use set, okay, which basically you're going to say the same thing instead of using the equal at the beginning. And for reading, some people they will even like split the line, something like this. Oops. And do the same here with sets. Sometimes just make it easier to read. Okay, and this is going to be the same thing that happened before. Another thing you can do to make it easier to interpret the errors that may come with your pipeline is use the check if exists. Just like we did before here, so from file pairs, it's a channel factory. Not only given the path, we can also just add check if exists true. And it's going to give a more Nextflow way of reporting the error, let's say. Okay. So now that we already discussed a bit this processes, this log info, some new channel factory, let's start coming back to a more like real pipeline thing. And that's this script 4, okay, which again has everything we've done so far. So the out here, we have the log info printing some information about the pipeline run. We have the index process that receives a transcriptome file, outputs an index created with Salmon. And now we have a new process. We're going to call it quantification, okay? This process basically has two inputs, which is a path to the Salmon index and a tuple that's going to have the sample ID in the reads, which is actually what you just saw, like gut and the two files, liver and the two files. That's what we have here is a tuple, okay? And it's going to output a path. And here, we just don't want like a Salmon index folder or some folder with a static name. We want actually a folder with the sample ID name, okay? So that's why we have the $sign here with the double quotes. And we're going to use Salmon again, the same tool, but with a different command here, which is quant. So really want to quantify that. Again, we're going to use the test CPUs, which by default is 1, but we can change here as a directive at the beginning of the process block and some other parameters, okay? Again, as here for the tuple, we have the reads. Because we know this is actually 2 elements, we can just call it here with reads 0 and reads 1, okay? And the output is going to be the sample ID as we already said here for the output. So here's for the command line. Salmon here is for Nextflow to know what's the output. And then, of course, we have our workflow block, which is going to coordinate all these things. So we're going to create a channel from 5 pairs. We want to check if it exists, and we want to give the reads path. And in the end, we're going to save this to a channel called read pair ch. Then we're going to call the index process to create the index. And then we're going to call the quantification process to quantify that. Okay. And then the output of that, we're going to save to a channel variable, which is quant_ch. So we can call Nextflow run script 4. Everything's going to work because we have Docker enable. It's going to really enable automatically Docker for us. One thing here is that it did everything again. And you know, here it's easy because we have few samples. It's like a toy example, but sometimes one process can take a lot of time, and you don't want to repeat everything just because you added a small thing at the end. So one thing we could have done is to add this dash resume. Again, because it's one dash, we know it's a Nextflow parameter, okay? So by using resume, what's going to do is that everything that didn't change from the last run is going to be cached. We don't run anything. It's much quicker. And new things will be run. So here, because everything has been run already, we're going to have everything cached. So the index was cached and the quantification was cached. If we had new samples, we would have part of it being cached and the new ones being run. Okay. One thing we can do is to use the tag directive. Again, directives, they are added at the beginning of the process block. Okay. So we can go to quantification. We're going to add here the tag Salmon on sample ID. And you're going to actually call it with all those samples, not only gut, but liver and lung also. Okay. Still, it won't change much here because we have one line being printed per task, per process, sorry. So we're going to see here while they're being done, but in the end, you know, you only see the last one. So one thing you can do is to use ANSI log false. It's a bit more verbose, but it tells you in more detail what everything is happening. If you have like 1,000 samples, it's going to be a mess, but here it's interesting because you know quantification on lung, on liver, on gut, and so on. But then where are all these files? You know, in here it doesn't appear like anything is happening. We saw already that they're going to be in the work directory, which by default is this one. You can change by providing -w to Nextflow. Okay. This last one, for example, was 74 for AA, and the file is going to be here. Okay. Okay, we can find it easily because we have the hashes and everything, but it's a bit annoying, let's say. Again, this is a toy example. It's easy, but sometimes it can be really like a monster pipeline. And this is a bit bothersome. So what you can do is to use another directive called published here. And by using published here in the quantification, for example, oops, we call it published here, the name of the directive. We say where we want the results to be published. And here we're going to use the out there, which is a parameter that we created at the beginning specifically for that, a path where we want our results to be. And then the mode. By default, what's going to happen if you don't say any mode is that a symbolic link, a shortcode to the file in the work directory will be created where we want in the results folder. By saying copy, we really want the files to be there. So if we run Nextflow, again, now we have the published directive. The files are going to appear inside the results folder. Everything was cached. So as you see here, I did 3 in the results folder, and now they're here, everything. So another step is to do quality control. This is something that's very common in pipelines. You do quality control, then in this case, you align or you quantify. So here what you're going to do is to look at this script file, script 5 file. Again, it has everything that we've been working on so far. So the output here, the log info about the pipeline, the index process, the quantification process, and now we have the FastQC process. We call it like that because there's an application of a software called FastQC that does quality control. So basically, let's first go to the workflow so that's clear to you what's the flow here. So we're going to create the channel with the channel factory. We're going to call the index process to create the index for that transcriptome. Then we're going to quantify that by using the index that was created and the read pairs. And then we're going to use FastQC to do quality control on the read pairs here. So here we don't depend on the output of quantification. So we didn't really have to do it this way, but that's the way we're going to do it here. So basically we just need the read pairs to do the quality control, because that's what we want. We want to do the quality control of the samples, okay? So there's a new process here, which is called FastQC. Again, we're going to use the tag to make it easier to understand what task is being run. So again, a process is the block, and when you run it, we call it task. So we have a task for every sample, okay? Every pair samples. Per file, sorry. The input is going to be, again, a tuple, which is the ID, gut, for example, and then the collection with the 2 paths, in case we call, in the case here, we call reads. And for the output, it's going to be a folder, the path, and part of the name of this folder is going to be the sample ID. It's going to be FastQC gut logs, FastQC lung logs, and so on. So here we have, for the first time, 2 lines in the script block. Like I said at the beginning, because we have 3 double quotes, this was always a multi-line string, so we could have many lines here. We're going to first create this folder because it doesn't exist, and then we're going to call FastQC by telling with the -o where's the folder, the format, which is FastQ, and then the reads path. Okay, so let's run that. This time I'm going to use the resume. Okay, to make sure that we don't have to do everything again. So it's a toy example, but if it was a lot of samples, it would take like forever. So we're going to use resume, and all the other steps, they already cached. Only FastQC is the new one, and that's what we're going to see here. So index was cached, quantification was cached, and then FastQC is not cached. We are running it. So here it's 1 of 1 for everything for quantification FastQC because we only have gut, right? So we could instead use like everything. Again with resume, telling all the 3 like gut, liver, and the other one, lung, and with ancilog of false, so we can see each one of them. So quantification on liver, quantification on lung, quantification on gut, they are all cached, as you can see here. And the FastQC, again, on lung, liver, and gut. This was cached for gut, but these 2, they were not because we hadn't run it before. So one of the tasks for FastQC was cached, the other 2, they were run. So this is something that you do at the beginning sometimes. The thing is, at the end, after everything is done, you want to have like a report of everything that happened, okay? So MultiQC is a very nice tool for that. It supports many different bioinformatics tools, and we're going to use that here at the end. So we're going to open the script6.nf, which again has everything we've been doing so far, okay? So here we have the tier, the log info. We're going to have the process index. We're going to have the quantification process. We're going to have the FastQC process. And now we're also going to have the MultiQC process. So we're going to use the published here, the params out we've set. We're going to use the mode for copy. Input's going to be a lot of paths. The output's going to be an HTML file, okay? And it's simply multi-QC space and dot in the current folder, and it's going to do everything for everything we've done. For the workflow block, we have everything like before, but now we also have this call for the multi-QC process. We're going to get the output of the quantification, which we called quant_ch. We're going to use the mix operator. So again, operators, they operate on channels. So whenever you have these functions working on channels, specifically for channels, they are operators. So we're going to use the mix operator to combine the channel quant_ch and fastqc_ch. And we're going to use collect, which is another operator to get everything and put like in a list. Okay, and then we're going to provide that to multi-QC. So in the end, what multi-QC is going to receive is a lot of paths. So we can run this and see what's going to happen. So again, a lot of things are cached. For multi-QC, nothing is cached because it was the first time we did. And now we can actually see that in the results, we're going to have multi-QC report.html. I think we can even open it. Results, multi-QC report. Oh, it's not rendering here. And Zoom is hiding the thing. Okay, anyway, in a browser, this would appear as a page and a very nice one. I cannot close it. Oh my God. Okay. So the next thing that we're going to do, let me close this file. So actually one thing we can do is this. So instead of calling multi-QC, let's inspect this channel. Okay. Everything is going to be cached, but the end, let's see. So as I was explaining when we had this, where is it? So the mix combines these two channels, the collectors in the list. So we have here, as you saw, the brackets, okay? And everything is just separated by commas. So we have the logs from FastQC for lungs, for liver, for gut. Then we have this folder. So we have everything that we generated so far just together in a simple list. And this is being provided to the scripts, to the multi-QC process that, as I showed before, it's just like everything. The input is just a path, many paths in this case, okay? So that's how it works. The thing is, as I said, again, this is a toy example. Sometimes this can take like forever. And one thing you may want to do is that, okay, so in the end, I want some customized message or even some email notification, okay? So you get an email when everything is done telling you, okay, your process finished. Sometimes it's not in your local machine, it can be in the cloud, or it can be in an HPC cluster, and you're not waiting for it to finish. You're doing something else and you want to be notified. So by looking at script 7.nf, again, everything that we've done so far, but in the end, we are calling this handler, this incomplete handler of the workflow, which means that whenever the workflow is complete, call log info. And if it's a success, again, it's another keyword here for the workflow, you're going to say, we're going to print a new line. That's why you have the slash, the inverted slash here, n. It's going to say done. So you can open the following report in your browser. So you click here. Otherwise, it's going to say, oops, something went wrong. And for email notification, you can even do that. So you can create this structure here with all the information from your SMTP server to send the email, and then you can send an email. You can have more documentation here. And a lot of things that I'm telling you actually can go to Nextflow docs.nextflow.io, and you have all the documentation with much more details, okay? So the idea of this training is to be very specific with a few things that we want you to see, but there are many more things in the official documentation of Nextflow. Another thing you can do is to have actually custom scripts. So our examples here, they were pretty simple in terms of the script block. So for the index process, basically we had one line, which is salmon. Then for the quantification process, again, we had like one line for salmon again. The FastQC, we had two. Okay, but again, they're very simple. Sometimes your script, they are much more complex. Maybe not only complex, but longer with more instructions. Okay, and that's what custom scripts are. So instead of writing everything in this Nextflow file, you could actually write it in a script file and call it from the script block, just like we are calling mkdir and fastqc and salmon and multiqc. We could call Marcel's custom script, for example. And one nice thing is that you can write your script file with Python or anything else, like a shell script, and you can put it in the bin folder, in the folder where the NF file is. And by doing that, Nextflow will automatically add this bin folder to the path so that it will be able to call your script from inside the pipeline script. Okay, so here we are doing that. We are making this fastqc.sh, which is this script here. We're making it executable. Oh my god. Okay, so we're gonna create the folder mkdir here with bin. We're gonna move it inside, and then by just calling fastqc.sh on your script block, you will be able to call it. Okay, so this is how you can work with custom scripts. Again, one thing that's important is that when you are doing that, you must tell if it's really a script language, what interpreter is going to be used to interpret that. So here it's Bash, but it could be a Python script. If it's a Python script, you would have here something like user and or being Python 3 or something like this. And then when Nextflow calls it, actually Nextflow is going to give it to the operating system to call it. It will know how to interpret that file because you have that's what we call a shebang. That you know the shebang and what software to call to interpret that. A very nice thing is that you can actually run some reports and metrics about your pipeline. So what we're going to do here is this long line, which basically is going to do everything we've done so far. So this pipeline that we built from script 1 to script 7.nf is actually the toy pipeline called RNA-Seq-nf that we created at Nextflow. So you can run it with the name, and automatically, because you didn't say any hub, by default, it thinks it's on Nextflow, and here it already knows it's nextflow.io. So it's going to download it from GitHub if it's not already downloaded, not cloned or pulled. It's going to run it for you. What's happening here? What's what happened here? Okay, this should work. Anyway, basically what we're going to do here is that we are saying that we want to run this with Docker. We want it to generate a report and the trace and timeline. So basically what it's going to tell you in the end is going to generate a picture for you with the directed acyclic graph, which is a graph of the connection that you have in your pipeline, like the processes, the input, the output, and so on. It's going to tell you how long each process took to be run, the amount of memory, all these things, so that you can trick your pipeline to be the most efficient with the resources that you have. So basically, that's what this all does. It generates an HTML report. Okay. I'm curious why this is not working. Let's look at the log here. It's a directory. Let's go to a different folder and run it there. Just make sure. Okay, I'm gonna try to investigate what's going on here and come back to that. Now we're gonna go to the next part. Let's actually take a 10-minute break. I think it would be ideal to have like a 10-minute break. I'm gonna investigate that, and then we come back, and I'm gonna talk about the dependencies and containers. Okay. 10-minute break. Okay, let's go back. So the first thing is that there was a change in the revision of the repository, so we have to set one that works. In this case, it's the -r dev. That's the revision of this pipeline. And by providing that, then the pipeline is going to work. It's going to pull from GitHub, and everything is going to run everything. As you can see, I call it here. It's still running, but it's going to do everything. Another thing that I forgot to show you, I tried, but was just the HTML code here. Wasn't the page rendered, and we can render that. And one way we can do that is that, one second, let's finish with ModiQC. Okay, so we can go to here to the ModiQC. Before it was just like that, the HTML, but actually we can click with the right button and go on show preview. And by doing that, we are really going to see the page rendered here, the HTML page. And here we have the ModiQC output, okay? With the percent of align, missing alignment, fragments, a lot of information about that ModiQC gives to you. But then we also want other things here. So we used in the command, we use with report, with trace, and everything. So we also have this report.html. And we're going to do the same thing. We're going to ask to render it. So show preview. And by doing that, we're going to see here the workflow report. And that's what I told you earlier. It has information about the CPU used by every process. We have 4 processes. So here we have a box plot of each of them. Okay. We have the percent allocated, the raw usage. We have from memory the same thing. So here the FastQC is the one that uses the most memory. Then we have ModiQC here. Sorry, FastQC, the ModiQC, and quantification index are very small footprint. But here is again is a toy example. We have not a lot of data. Okay. We can have the job duration. So FastQC by far is the one that took the longest compared to the other ones. ModiQC a bit, but FastQC took a lot more. We have here input and output, so number of bytes read. Okay, we had tasks, each one was completed or not. The allocated CPUs, we went by default, so it's 1. So everything. Here we have 6 entries. Okay, so the number of processes and the number of time it was called for every sample. So it's nice to have that because sometimes people ask like, oh, so what's the number of CPU that you use? How much memory I should request from my HPC cluster or from the cloud? All these questions that actually it's very difficult to answer if you have never run your pipeline. But by using these reports, you can keep tweaking, adding more CPU, less memory, and in the end, you have the machine, the specifications to request that are really tied to how your pipeline works. So these reports, they help a lot with that. One thing you can do is to run your project from GitHub, as you just saw. So you do that, it automatically is going to think it's GitHub. If you want, you can use the -hub, and it's going to tell you what hub to use, if it's Bitbucket, GitHub, or Git and so on. Here we're going to use the revision from dev, as I showed before. Again, there are much more documentation and details about everything that I said so far and much more in the Nextflow official documentation page, which is docs.nextflow.io. We have this Nextflow patterns page, which is very nice. It's a collection of implementation of processes that are a bit more tricky, but they often come up. So how you do a process collects output from many different processes, like we did with ModiQC here. It's a Nextflow pattern. So many things that you cannot do at first because it's a bit complicated, someone has already faced that and created a Nextflow pattern for you to look, and you can check it there. Now, the last section of today, which is the section 4 with managing dependencies and containers. This one is very interesting. It's tied to many things that Evan said at the beginning about reproducibility and isolating environments and so on. I talked about Docker and Singularity. So here we're going to do a very quick introduction to how to use Docker, okay? So Docker is already installed and running in this Git pod instance. So basically, you can just use Docker run and say any container name. So here, reload world is a very, is a very common to use it the first time that you're using Docker. Here, as you saw, when I type the name wrong, incorrectly, it's going to try to pull from the internet. It can find it locally, so it's going to try to pull from the internet, but then doesn't exist. But for this one, which exists, again, it cannot find it locally, but then it can remotely, and then it pulls it from Docker Hub. And here it's running. So basically, you have hello from Docker. This shows that your installation appears to be working correctly, and so on. It's a toy container image, so there's not much to do here. If we really want to use a real one, we can use, for example, a Debian image. Debian is a Linux distribution. So here we want to not run for now. We want to pull, like download. And the tag is stretch slim, because I can have many different versions of a container image. So here's a version of Debian, for example. So by using Docker pull, I download it. So here it says downloaded the newer image for Debian stretch slim from here, which is in Docker Hub. If you type Docker images in your command line, you're going to see all the images that are downloaded in your machine. So here we have all these images. Okay. If you want to run it, you already saw. You can just use Docker run and the name of your image, and then what you want to do inside. So when we use the hello world, the image was created in a way that's going to print some content to us. But here we don't only want to do that now. So now actually I want to run a container to have a terminal and to interactively interact with it. And then we're going to call bash, which is a shell, the terminal for me to interact with this container image. By typing that, we are inside it. So we are not in our machine anymore. I mean, we are in a machine, but we are in this isolated environment, which is a container being run. Okay, so we already know how to download a container image and how to run it, and how to run it interactively so that you can do things inside. But it's not very useful if you want to change things, because when you kill a container image, when you kill a container, everything is lost. The information there is not persistent. You have to create in a way that it is if you need it. But here we don't want to use only container images that other people created. We want to create our own. So here one example is to use a Docker file. So I saw some people commenting why I'm using vim as an editor here. So I could simply do the Docker file and right here. But I could also come here. And the thing is, the zoom thing is always at the top, bothering me. So I could come here and create a new file. Okay, it's here. Create a new file and call it Docker file, for example, and then I would write it here for you. It's the same thing. I'm just using the vim here because when I'm writing with this dialogue here, I lose the content that I'm trying to show to you here. And while I'm typing, some people may want to read what's in the training material, in the transmission, in the broadcast. So by typing here in the terminal, I make it easy for people to still follow what's being shown here. Okay. But you don't have to use vim. You can use anything you want. So here I'm going to create a Docker file. Okay. And I'm going to basically copy paste to make it quicker, but I'm going to explain everything to you. So basically in a Docker file, you can have a maintainer field, which is your name, the creator of the container image. But here I'm just going to ignore that. Then you tell every line is a layer. That's how we call it. So the first layer we use from, which is the base image from the very beginning where we're going to start. Usually, as you saw in Evan's talk, container images, they're much smaller than virtual machines. And the idea here is that depending on what you want to do, you want a very, very light and simple image to start building on top of it. So here we're going to use the stretch slim Debian. It's a small image. And we're going to run one layer, a command, which is basically going to update it and install curl and calsay, which are two softwares, okay? And that's going to give some environment variable, okay? Here, path. I'm going to add, actually, to the path, the /usr/games. Once we have the Docker file, we have to build the image, okay? Basically, we're going to use Docker again, but the command this time is build. And then we have to give a tag or a name to this image. I'm going to call it my image. And then you have to give this dot at the end to say that the Docker file is in the current folder. So create an image based on this Docker file. And by doing that, in the end, we're going to use Docker image again to see all the images that we have in the computer, images. And my image is now here. So we didn't say anything, so the tag is latest, has an ID, created 7 seconds ago. The size, 130 megabytes. And again, we're going to use Docker run to run our container. So the name is not hello world. Now it's my image. And instead of bash to interactively enter, I don't want that. I want to run calsay, which I know is installed because I set it to be in my Docker file. And then I'm going to give a parameter, an argument for this calsay software, which is a phrase you do. And a cow is going to appear and say something. So here, it's not, this calsay is not running locally. I mean, in this environment we are using, it's actually inside a container inside the machine that we are using. Okay, so it's isolated. And this guarantees that other machines in your computer, on the internet, in the cloud, in the HPC, is going to use this container, and we're going to get the same result. But again, just using curl and calsay is not really a lot of things. We want to do more things. What we're going to do is to add this line here. Again, I'm going to copy paste to make it quicker. And I'm going to use the curl, which is a software to download things, download files. I'm going to download Salmon. And I'm going to move Salmon to this folders that are already in the path of the operating system. So when I say Salmon, the container will know where Salmon is. Okay. And you probably can see here that I'm using curl, I'm using tar to uncompress it, and I'm using move to move it somewhere else in the system. There's a lot of commands, and I'm using a single line. So why don't I have many different lines? I have to run with curl, run with tar, run with mv, run with mv again. The thing is, as I said earlier, every line in a Docker file is a layer. And the more layers you have, the larger it's going to be. I mean, it's not only going to be larger, but it's the way Docker works may be a bit slower because it's going to download per layer. If you change one layer, it's going to, even a tiny thing is going to change, it's going to download the whole layer again. So the way you do that, you have to think wisely if you want to have one run expression with a lot of things or many different runs. If, for example, you have one run with installing many different packages, it's not very ideal because, you know, sometimes you want to change only one package and the whole layer will have to be downloaded. And if it was separated runs, only the last layer would have to be changed. So, you know, you have to think on how to do that. It works both ways, but sometimes it's better to use one way or the other, okay? So by having this here, now adding Salmon, again, I'm going to build my Docker image. Minus T, I'm going to say the same name again, and dot because the Docker file is in the current directory. So it's going to do a thing. If it was pulling from the internet, the first part wouldn't have to be used because it was already there. Here it was much quicker than the first time, for example, because it already did everything else. And now I can do the same thing I did before with calsay and bash. I can just run my image. I'm going to call Salmon, and I'm going to give an argument -- version. And we can see here the output, which is Salmon 1.5.2. But if I type here Salmon version, oops, comment not found because Salmon is not installed. So I'm saying this just to make sure it's clear to you that Salmon only exists within this container that we created. It doesn't exist here in my normal environment. Okay. Another thing you can do, as we did before, oops, is to enter interactively in my container and play with Salmon from inside. So here, if I do Salmon version, it will work because I'm inside the container. But as soon as I leave the container, I cannot use Salmon anymore. Okay. A few minutes ago, I was saying that, you know, things you put inside the container, they don't persist. They are isolated. So if they're isolated, how can I create files there or here and make them read and so on? What we're going to do here is do something that is very similar to what we've done before, which is Docker run my image. I'm going to call Salmon. I'm going to call index, and I'm going to give the path to the transcriptome reference file that we used in the RNA-Seq pipeline, okay? And the output is going to be the transcript index. This is not going to work. And the reason this is not going to work is because even though we know that here in data, GGL, and so on, we have this transcriptome.fa, inside the container, it doesn't know where is that, you know? So here we can go to data, this, and then we see that. But in the container, it doesn't. So what we're going to do here is to create a volume. So again, Docker run, but then we're going to do -- volume. We're going to say, you know, this file here in my local machine, I want it to be here in the container image. And then I'm going to say the image I want to run, the command, and so on. And now it's going to find. But again, everything happened inside the container, so I don't have the output of this command. To do that, I have to do the other thing. I have to also say that what's there is here. What's inside the container, I want to be here. So this time, we're going to use a larger volume. I'm going to say like my working directory, the directory I am right now, is going to be the same thing there. The work gear is going to be here, my image, and everything else. And by doing this, the container will see the transcriptome.fa that is my local directory here, and I'm going to see the output that was generated there, which is for the transcript index, okay? As we said here. There are other ways to do that, but I mean, you're free to get into the other details that this way that could be done. Here's just one example. As I said, you can see everything inside the folder. This is locally. So it's a very simple container image, but I could have, a very complex one, and everyone in my lab want to use it, or at the company, or want to ship to clients. So it's just locally now. So one thing we can do is to push it to Docker Hub or to any other image repository like quay.io. And by doing that, anyone can pull from that container image repository, just like we pull the Hello World example or the Debian one with Docker pull. Anyone can do that. So I'm not gonna do it here, but basically you have to create an account in Docker Hub. You're gonna log in, you're gonna tag, and you're gonna push. Instead of pull like we did before, we're going to push our image. And by doing that, anyone can pull it the way we did with the Debian one. Okay. So we did it before using the image. So when we had the nextflow.config, we saw here the process container, we said nextflow/RNA-Seq-nf. We could do now is having like your username is /my image. So this is something that you can do in the break or tomorrow or today after the training and ask questions. So the channel for questions on Slack is not only for questions during the training. Today, after the training, tomorrow, all these 3 days, you're free to ask questions there, and we're going to do the best to help you. So you can try to redo everything I did here. You are free to do this part, like pushing an image that you created to Docker Hub or Quay.io, and then using it with Salmon for the script 2 and F. So to remember what's inside the script 2, it's just the very beginning using Salmon to create an index, okay? So here we're going to use a different container image, which is the one you will create by following these instructions, okay? Another thing is that it's not only Docker that you can use to have container. You have Singularity, you have Charlie Cloud, you have Podman, you have many different technologies for working with containers. And depending on your infrastructure, one can be preferred over the other. So in HPC clusters, usually people prefer Singularity or Podman over Docker. In the cloud, it depends. So you can really, and they are very interpretable. So images from Docker can be run with Singularity, with Podman, and so on, okay? So here, let's go to this section on Conda. So another thing you can do, actually, is to use Conda to install. So we were using apt-get when we were looking at the Docker file. We were using apt-get here to install curl and calc, and then curl to download the binary of Salmon. In bioinformatics, it's very common to use Conda to install applications. And not only that, but to create environments in your machine where you can run these applications, very isolated ones, even though they're not even close to containers in terms of isolation, but they're much better than just running locally, okay? So basically what you can do is that you can write a YAML file with instructions for Conda on how to install this environment that you want to use, okay? So you can create this env.yaml. Here it's already created. So basically it has a name of the environment that you want to name in your machine, the channels of Conda that it's going to use to look for the software that you want to install, and here are the names. So here you have Salmon, FastQC, MultiQC. Here we have, I want specifically from this channel because some channels may have the same software. You can tell the specific version that you want. And by having that, you can create your environment by typing Conda and create, and you pass the YAML. So it's going to collect package metadata, the dependencies and everything, and it's going to create this environment and install all the software that you requested, which here are Salmon, FastQC, and MultiQC. This may take a while. I'm going to keep talking while it's doing that. Actually, it's better to wait a bit. But the idea here is that you're going to download this softwares, install it in the place in your computer, so that just like Salmon, when you call Salmon in your command line, it won't find it because it's installed in an isolated environment. So you can use conda env-list to list these environments, okay? And you can use activate with the name of the environment. The one we just created is nf-tutorial. So by doing that, it's going to activate your environment, and now you can call Salmon and it's going to be found. It's not going to tell you command not found. It's really going to work. And with that, we could run the script 7. That's like the final script with the whole RNA-Seq pipeline that we created in the section before. And by saying with conda and telling the path of the environment that you created, here is nf-tutorial, it will use Salmon, even though it's not installed normally, let's say, in this machine. It's installed in a conda environment. So if you don't want to use containers, you can use this to have the installed software isolated in an environment in your machine. But still, this is not really a good practice for reproducibility, because you still have a lot of other things in your computer that can mess with that, okay? It's taking too long here. Another thing you can do is to use Mamba or MicroMamba, which is very related to conda, to install these packages. And MicroMamba is much faster. But apart from that, it's very similar to conda. So the same way we have these YAML files, all the dependencies channels, the name. But I think here what we're going to do is that we're going to write a Docker file. And instead of using curl or wget or apt-get, we're going to use MicroMamba to install all these packages here. And then we're going to use inside our container, which is a very isolated way, a very reproducible way of installing software, which is with MicroMamba. I want this software here, like FastQC, in this specific version from this channel in a conda repository installed with MicroMamba. So you can really take control of how it's installed. And because you're also using a Docker file, because you're using a container technology, it's also isolated in this sense. It's very reproducible. You can share your image and everyone can reproduce what you did. So that's what we're going to do it now. We're going to create this Docker file here. So you saw that it's still finishing to create the conda environment, but we're going to create this here. It's taking longer than usual. I'm going to create another terminal here. Create this Docker file. It's going to have MicroMamba now. Let's put here just so that you know how you could do it. So I'm gonna have this. I'm gonna copy the YAML file that we have with the instructions to the container image, to the container. I'm gonna create this environment. I'm gonna install, I'm gonna clean, and tell the container where these things are. So before I have to create my MicroMamba YAML file. I can build my Docker image. We go to the other terminal, so it finished. It finished creating here. I could activate my NF tutorial. So here, as you see, there is no summon. But if I activate, what was that? What was the name? INF tutorial, I think. Okay, closed in the end. So here we're creating the micromamba, the container image that have everything installed with micromamba. And with that, we can just call, after building that, we could run the script7.nf with Docker by providing this image that we just created with micromamba managing the installation of the packages. So this is taking a long time just to do that. I will skip this and go to biocontainer so we can end, which is the last subsection of our fourth section on dependencies and containers. So biocontainer is very interesting. So you see, you said, okay, Marcel, you said that Conda is used to manage these installations in bioinformatics. We have containers to have real isolation, but the Conda and Macromamba, they manage very well the installation. So the best way is to do what you just did, which is to create a container image with Docker or Podman or something else, but manage the installation of the packages with Conda or Micromamba. But I don't want to do that all the time. Like every time I want to have a container image with this and this package, I have to create everything. I don't want to do that. So the biocontainers is a project that was created to have it ready for you. So you can just go to the biocontainers project website and look for container images that are already there with the software that you need already installed. So for FastQC, for example, we already have a biocontainer that already has FastQC installed inside. And actually, you can look for other biocontainers images that have everything you need, and then you don't have to create anything. It's already there, very lightweight, very simple, with the only things that you need. So here what we can do, for example, is to run the script2, which again is the very simple creating index process that we created at the beginning of this session today. But then I want to use this Docker container, which is the biocontainer that has Salmon. Was the wrong folder? So now the script2, you remember, it's only with the index process. You're just calling Salmon once. So the only software we need is Salmon. So I'm going to use a biocontainer that is very lightweight, but has Salmon inside. And then it's going to work. Again, even though Salmon is not installed in this machine. So when this is finished, I'm going to run Salmon, and you're going to see again, command not found. But here I'm saying use this container image Docker. So again, Salmon is not installed. So there are some bonus exercises and some other exercising contents here that you can check. So I really suggest you to go over the whole training today with the things that Evan and I showed. Okay, feel free to go to the Slack channel and ask every question that you have. No question is simple enough. So there's no problem at all. It's a lot of people who are really looking forward to reply to your answers. And